Wasabi, you guys. Welcome to Integration B for Intermediates Part 20. In this section, we're going to learn about the beta function. If you remember, we talked about the gamma function, or, well, the factorial definition of the gamma function. But to just kind of recall, this is the gamma function, and this is equal to x minus 1 factorial. Okay, it's not x factorial, it's x minus 1 factorial. If you would want x factorial, then this would be the gamma of x plus 1. Okay, so just be very careful about that, right? The gamma of x, x minus 1 factorial, gamma of x plus 1 is x factorial. Okay, I believe you can also rewrite this as x gamma of x, because this is equal to x minus 1 factorial, which is indeed equal to x factorial. So you can also keep this in mind as well. But yeah, I just want to kind of recall this gamma function, because normally we just stick with the factorial definition rather than the gamma function. So now, what is the beta function? The beta function is defined like this. With the beta, two variables, x and y. It's defined like this, and the beta function is equal to gamma x, gamma y, and then gamma of x plus y. The reason why I put it in gamma function is because this is a lot easier to see. It's a lot easier to memorize. If I put it in factorial definition, it's going to look weird. X minus 1 factorial, y minus 1 factorial, and then x plus y minus 1 factorial. So all these minus 1s, or the factorial definition, it's like if you don't memorize it by heart, you can screw yourself up by thinking, oh, it's x factorial, y factorial, or oh, I remember it's x minus 1 factorial, y minus 1 factorial, but then you're like, wait, is the bottom x minus 1 y minus 1 factorial? So minus 2 factorial, and so on, and you get mixed up, and it's just it's terrible. So unfortunately, I hate this new paint. Okay, so we would stick with this so that after it's easier to memorize it in terms of gamma, and then you can turn it into factorial. So that's just my approach, is like it's easier to memorize the definition of beta in terms of gamma, and then once you got it in terms of gamma, you can go ahead and put it into factorial form. We also know that the gamma of n, or n minus 1 factorial, okay, it's not n factorial, this is n minus 1. Okay, this is n minus 1 factorial. So we learned about this in the previous section. So then, what does beta look like? What does beta look like? So beta looks like this. From 0 to 1. From 0 to 1, we have m minus 1, 1 minus x, n minus 1 dx. Notice that it's like, just like gamma, we have to do the minus 1, n minus 1 factorial, right? That's exactly how beta is like. So for beta of m and n, we must utilize n minus 1 and minus 1. Okay? And in this beta integral, it doesn't have the exponential function. It's just x and 1 minus x. And that's it. Okay? So, in fact, there are 3 forms that we must know. Right? It could be either way. Like if you let 1 minus, this could be either way. It doesn't really matter. It could be 1 minus x and minus 1. Right? If you let u equal 1 minus x, it's going to equal the same thing. So it doesn't matter which way. As long as it's in this format, you can put it in beta function, and then you can just dive right into solving it. Okay. So that's the first form. Our second form. You don't really have to memorize this because this could be easily trig sub, pretty much. This comes from trig sub. What happens is this. Let me write this in. Let's call it. This comes from by letting x equal sine square theta. Okay. Let x equal sine square theta. Then you get our second form from 0 to pi over 2. And you would get 2 sine of 2m minus 1 theta. And then cosine of 2n minus 1 theta. d theta. This is the second form of the beta function. Again, I feel like you don't really have to memorize this one by heart because you'll rarely come across this. And even if we do come across this integral, we could just let, x equals sine square, and then you can put it in terms of this. Right? So this is just a trig sub of the first form. So you really don't need to memorize this. Okay? Alright. The third form you must memorize. The third form. The third form goes from 0 to infinity. From 0 to infinity, the beta function equals to this integral where the top is x to the power of m minus 1. The bottom is 1 plus x m plus n dx. Now, this, I'm going to color this. This is the golden formula. This is the golden formula. This is the integral that you will most commonly come across more than the other 2 forms. And the reason is because this integral, a lot of problem writers of integration B, they will use this as a skeleton. And what I mean by that is they would use this integral and then modify it into something like let x equal whatever, and it would become like a u sub in the form of this integral. So it's very sneaky, it's very hard to see, and yeah, you're gonna come across this integral a lot more. So this and this I would just suggest to just memorize by heart, and you'll definitely be okay. Alright, now that we know how the beta function works, well, it's just a formula, but now that we know how it looks like with the format of it, let's go ahead and start solving some integrals using the beta function. Let's say you're in a beginner level integration B and you come across this integral. Most people would just let u equal 1 minus x or something like that. But you would have to, that would force you to express a long polynomial, and we're not going to deal with that. So, to beat our opponent very quickly, we would use the beta function. Now, be careful, this is not 5-4. This is what? The format was n-1, n-1. So this is equal to n-1, and this is equal to n-1. That means that we are adding a +1 more. So this is 5 plus 1, 6, 4 plus 1, 5. This would be our beta function. Okay, so this is equal to gamma in terms of gamma, so that it's easier to not lose track. And then we can comfortably put it in factorial form. Okay, this is 5 factorial, 4 factorial, and this is 10 factorial, right? And then you can also, in most integration bees, they won't allow you to have a calculator. So you'll get like 4, 3, 2, 1. 5 factorial will cancel out with some of the tens. Some of the terms in 10 factorial. So up to 5, there you go. This is 6. And then this becomes 2. And then you get 90. Well, actually, what's 9 times 7? 63. 63 times 2, that's 126. So that's 120. So the answer would be 1260. The bottom. This tells me how ugly this polynomial could have been if we were to do it regularly. This would have been a nightmare, and then plugging in the bounds from 0 to 1. That's a nasty fraction. You'll have a lot of nasty fractions. So, that beta function saved us and got a much cleaner answer. So we are given a trig integral. You could just do basic u sub, or we can utilize the beta function. Now be very careful. With the beta function, you need the 2, just like before. And I guess to sort of simplify it, you can let u equal sine square. Let u equal sine square. And what that does is this would give us 2 sine x cosine x dx. Okay, so we would need that from 0 to 1. See, so we take away, so we need a half. And we need to take away 1 of sine of x, 1 of cosine of x. So this would give us u, and then 1 minus u, which is cosine square. There was, I guess I'll slow down, I guess. So taking away 2 sine x cosine x, we're left off with this, and this could become s squared 1 minus s squared cubed. And so that's how I got to this integral. And now it's a lot easier for us to see that this is just a beta function. You can actually do another substitution by doing 1 minus u again, and then you'll be left off with like w cubed times 1 minus w, and that's also very easy to integrate. But for now, because this is a beta function, let's go ahead and practice our beta function. This would be 2, 4. And then putting it in factorial form. I think we saw how this goes. 1 factorial times 3 factorial. And then 2 times 5 factorial because of this 2. Okay. And now we have, let's see, that's going to be like 1 over 40. Okay. Now, if we were to do this with a u substitution, like let u equal 1 plus x, this would have been torture, because then you would have to actually express like u minus 1, and then a bunch of polynomials terms dividing everything by 1 over u to the power of 7. It's disgusting. It's a disgusting u sub process. So with beta function, this would be a lot faster. Now, how was the formula? How does the formula go? What's the format? Do you remember? So the easiest thing was, we know for sure that this is n plus n. That's very easy to memorize. But what's at the top? The top is m minus 1. M minus 1. Okay? So if this is 4, then that means that our m must be 5. And this is 7, and m was 5, then n must be 2. And that's how we go about this. Alright, now this is just, let me try not to lose track. Okay, so then this is 4 factorial, 1 factorial, 6 factorial, right? And this is just equal to 1 over 30 because the 4 factorial cancels out. So it's 1 over 30, and that's our answer. You see how quickly that was? How fast, and then versus doing u sub was disgusting, right? You have to deal with so many coefficients and reciprocals, and it's tedious. Here with the beta function, we can just dive right into factorial form, and then bam. The only thing we just have to work with is just finding variables, and that's it. Okay? Is this a beta function integral? Not exactly, no. But we can make it turn into one. We can turn it into one by letting u equal x squared. Right? And now this could just be a half integral from 0 to 1. So now what we have here is u squared 1 minus u squared du. So now we have this, and now it's just a simple beta function. This is just a half times beta of 3, right? Okay, so this is just 2 factorial, 2 factorial, 2, this cancels out. And then gamma of 6, which is 5 factorial. The 2 factorial cancels out. So we are left with 1 over 60. Okay. With this integral, we can clearly see that we just need to let u equal square root of x. And now this would give us 0 to 1. So we know we're going to have to use a 2u. But then, let's see, u to the power of 6, so this would be to 7. And 1 minus u, power of 5. Let's just go straight into beta function. This is just 2 beta of 8, 6. Right, so now this is gamma 8, 7 factorial, gamma 6, 5 factorial. 8 plus 6, 14, 13 factorial. Okay. This is a lot, actually. 2 times. Actually, let's put in the 2 with it. 2 times. We know 7 factorial is going to cancel out. And then we're left with like 13, 12, 11, 10, 9, 8. And then 7 factorial cancels out. This is 4 times 2 is 8. 2 times 5 is 10. We can make this a lot simpler. How can we make this a lot simpler? I guess we could just use that, do times 3. Okay. So then in that case, let's see. This is nasty. Honestly, we could just leave it like this. I mean, if someone were to write it like this, you know, I think this is okay. You can just leave your answer like this in factorial form. Oh shiz! Do you remember? Do you remember the format of this integral? It was 1 plus x n plus n x to the power of n minus 1 dx. Okay. So then this means that our beta function is 10, 11, 10, 11, 10, 11. Okay. So that means that we have the gamma of 10, 11 squared divided by the gamma of 2022. So in that case, we could just leave our answer 10, 10 factorial squared 2021 factorial. You just leave your answer like that, and you're pretty much good to go. Whoa! Alright, now we're getting into some serious business here. This kind of looks like the beta function, but our beta function is defined as this format here. 1 plus x, n plus n. This is the beta function. This is the beta function. But this does not look like that, right? There's no x on top, and this is x to the power of something. And that's the first degree. So how can we use the beta function on this? Well, the first step, the greatest first step to formatting this into a beta function is to make sure that the bottom is 1 plus x. 1 plus x, and then to the power of something. Here we have x to the power of something, the golden ratio. So what we would want is we would let u equal x to the power of the golden ratio, so that this would be a 1 plus u to the power of something, and then whatever. Okay? Alright, so then in that case, u is equal to that, du is equal to the golden ratio, x to the power of golden ratio minus 1. Okay. So what would that look like? It's going to look very intimidating. So we have 1 over golden ratio. I'm going to actually... That looks... Okay, that actually bothers me. Wow. That actually bothers me. Yeah, I'll go like this. I hate the new Paint program, I swear. Okay, so let's move this here. Oh my god! I swear, whoever programmed this, such a nuisance. Okay, so we let u equal x to the power of golden ratio, and we end up with, let's say, 1 over phi, and then du, but we need to do the x over to the power of phi minus 1. First off, let me actually write this part here so I don't forget. And then our leftover was, let's see, du, we pretty much have to bring it to the other side. Or I guess the best way is to sort of use a force u substitution. And you should get 1 over phi minus 1. I think a force substitution would be an easier way to look at it. I think that's the easiest way to look at it, is a force u sub, because we don't have anything to exchange with. Okay? So we get this. Now, Now this is, oh well, that du, let me make it easier for you to see. There you go. Close enough, close enough. But it's a lot easier for you to see how this is a beta function now, right? This is 1 over phi beta function of, well, this is n minus 1. 1 over phi, and then m plus n. This is m is 1 over phi. Here, m plus n has to equal to this, but we know this is 1 over phi, right? So what's n equal to? 1 over phi. Okay, so this is phi 1 over phi. Okay, got it. So now what? Well, this is equal to gamma 1 over phi, and then gamma of phi of 1 over phi. And then, if you notice, if we add it together, we get gamma of phi at the bottom. Now, oh crap, ooh, be careful, we have 1 over phi. Don't forget about that. Now, the reason why we use in terms of gamma is because factorials are only used when x is a positive integer. Or not, I shouldn't say that. A non-negative integer. Non-negative integer. So, maybe that's not the right form. I think the safest way I should put it is like this plus, plus 0. Okay, so this x factorial is only defined for non-negative integers. Okay, that is why we use gamma, because these are not integers. These going ratios are irrational number, right? But however, gamma functions, even though gamma function is technically a factorial type of function, this you can plug in any real number. That's what that gamma function is. That's the difference. So, obviously, we don't know, the factorial of the golden ratio, because that's just disgusting. I forgot I can't do that. I have to go like this. So, what does this equal? Well, let's just keep simplifying. Let's keep simplifying. Slow down. Let's keep simplifying. I have something to tell you. This golden ratio has a special property. If you solve for x, x is equal to the golden ratio. If you solve for x in this quadratic equation, x is equal to the golden ratio. Well, one of the roots is. One of the roots is. And because of that, that means that this is equal to 0. And if this is equal to 0, then this is also true. The square of the golden ratio is equal to the golden ratio plus 1. And if this is true, then we can divide both sides by the golden ratio. And if that's true, then this is equal to 1. So what this means is that this here is equal to 1. So we're left with just this. 1 over factorial here. I mean, not 1 over factorial. 1 over phi. And then this. Okay. But wait, but what is this then? 1 over the golden ratio? 1 over the golden ratio. Oh, look at this. 1 over golden ratio. 1 over the golden ratio is equal to phi minus 1. Oh, wait a minute. phi minus 1. Do you remember this? Remember when I said that the gamma function can be put in terms of, what is this equal to? This is x minus 1 factorial. X factorial. What is x factorial? The gamma of x minus 1. This means that this here is equal to the gamma of phi minus 1. Ah, yes. I'm not joking. This whole integral is equal to 1. This integral is equal to 1. It's not a joke. You don't believe me? Put in Wolfram Alpha. It will tell you it's equal to 1. Very cool. Very satisfying. I think we learned some extra material here about how to utilize the golden ratio. It's very nice. Very cool. And I think it's also, I like this example because it helps us remember this property here. This useful property here. I think we know what to do here. We already know what this looks like. A beta function. So let u equal e to the x. And this will give us 0 to infinity. U to the power of 4 du. 1 plus u to the power of 7. Yep, this is now equal, let's see, 5 plus something equals 7. 2. So our beta function is just 5, 2. And this is just equal to, I think we've done something like this. 5 factorial. 2 factorial, that's, sorry, gamma of 2 is 1 factorial. And then 6 factorial. Yeah, this is just 1 over 30. Okay. Ooh, so usually, most people would just do trig sub. Let x equal tangent theta, and then just dive right into trig sub. If you try doing trig sub, what would that look like? Because I'm curious. Let's see, secant square theta. If you do trig sub, you get secant square secant 8 theta, which gives you, let's see, from 0 to pi over 2. Right? And cosine of 6 theta. Honestly, this is actually a lot easier. So much easier and faster. I actually wouldn't use beta function. You could use beta function, let u equal x squared. Right? And you would just get like 0 to infinity. U minus half. U plus 1 power 4. And then you would just have to do, but then you have to deal with like fractions. Right? And then it's just, you know, a lot of this, whatever, and it's just you'd have to do some computational stuff here, right? Here we could just dive right into Wally's product. So in this case, this is also a good example where sometimes it's easier to just do trig sub rather than the beta function. So yeah, sometimes it's just easier to just use trig sub rather than beta function. So in this case, instead of using the beta function, we would just go straight into Wally's product. Pi over 2. This would be 3, 4, 5, 6. This is equal to 15 pi over what? This is 8 times 48. Would that be correct? No, that's not 48. No, that's not. 16 times 6. And then you can simplify this further. Divide by 3. This would be 32. 5 pi over 32. Right. If you were to do beta function, this would be ugly because you would have to do with like halves. I guess. But here, in this case, we can just go use trig sub and do Wally's product. Okay? This does not look like a beta function. Right? You would freak out. You would freak out and say, this looks nasty, what do I do? So let's calm down. Let's calm down. Notice that this is a negative exponent. So this would be something like this. Okay. So that's a good sign that this could possibly be a beta function. And in order to see this, let u equal x squared over 2, so that this whole thing is just 1 plus u to the power of something. And so now in that case, doing this u sub would give us, so from 0 to infinity, this would give us 1 plus u, 3 halves. I just noticed if we do 2, we get x. We would have to have, let's see, x is equal to square root of 2u. Again, we don't have anything to exchange, so you have to do a forced u substitution. So in that case, we have root 2 here, and then u to the negative half. It's because x is equal to square root of 2u. So, now that we did our forced u substitution, we can now go ahead and dive right into our beta function, because this is in a form of beta function. This is a form of beta function. It's just it's an ugly form of beta function. So, okay. Let's go ahead and do that. So we have 1 over root 2. Don't forget that. Let's see. And then m minus 1. M minus 1. This is equal to m minus 1. Then plus 1. So this would be a half. Okay. Then a half. M plus n. So n would be 1. Okay. Thank God, this is not as bad. So then in that case, we have 1 over root 2. We have the gamma a half. We know gamma 1 is 1. And the gamma of 3 halves. Right. Again, we can't put this in factorial form because these are not non-negative integers. So, we have to do some manipulation here. So, 3 halves is equal to a half plus 1, right? What do we do to this type of form? It's this property, right? The factorial property. So this is equal to a half times the gamma of half. Aha! So this means that, let me clear this. So this means that they actually kind of cancel out here. So this is equal to 1 over root 2 gamma of a half and gamma of a half. This cancels out. Aha, so this is equal to the square root of 2. Okay, and that's it. That was our last integral. One last note: if you come across gamma of a half, a gamma of a half is equal to square root of pi. So this is also, keep in mind of this, right? The best way to prove this is to think about the Gaussian function, right? Think about the Gaussian function. Just treat it like square root and then do some u substitutions, and then it'll become a Gaussian function, and the Gaussian function will give you this answer. The Gaussian integral will give you this answer. So the gamma of 1/2 is equal to the square root of pi. So keep that in mind. Okay? But other than that, that's pretty much it. that's the beta function. So, yeah, I hope this is very helpful, and good luck if you have any integration bees coming up. Other than that, I'll see you guys in the next part.